In my last video, I introduced the two major bottlenecks that slow your program down: compute bound and memory bound. At the end of the video, I mentioned a specific compute bounded task, which is general matrix multiplication. This operation, despite its apparent simplicity, can be remarkably challenging to optimize efficiently. In today's episode, we're going to walk through some genius algorithms to make it over 100 times faster, all achieved through pure CPU optimization techniques leveraging SIMD and cache strategies. Some of these techniques might seem counterintuitive at first glance, but they'll start to make perfect sense as we delve deeper into the underlying reasons. We'll begin by implementing a vanilla GEMM algorithm. This straightforward approach involves a triple for loop structure to compute the dot product for each entry in the matrices. Here, we simplify the input to be square matrices of size mat size. The performance of this basic implementation is notably slow, taking approximately 2 seconds to process matrices of size 1K by 1K. Of course, we're not even using multi-threading right now, so let's do it with the OpenMP parallel for macro. It seems that we've already accelerated the algorithm by a factor of 10. This is because my CPU boasts an 8-core 16-thread configuration. However, despite this improvement, the important question right now is it really fast enough? We are going to optimize an algorithm. When should we be satisfied? To understand this question, we have to do the math first. According to Intel specifications, my CPU has a maximum compute bandwidth of 600 gigaflops. The memory bandwidth limitation stands at approximately 46 GB per second. However, keep in mind that memory bandwidth isn't solely dictated by your CPU. Peripheral factors including lower memory frequencies and underutilized memory channels can also decrease your practical memory bandwidth. To test the memory bandwidth in the production environment, we turn to the stream benchmark. According to this benchmark's result, my system's practical memory bandwidth ceiling hovers around 21 GB per second, equivalent to 5.25 gigaflops. The next question is, we all know that GEMM will eventually become compute bounded from the last video, but when? The answer, theoretically, isn't overly complex. Since we can find out the total number of memory access to be 3n squared and the total number of floating point operations required is 2n cubed, GEMM should shift from being memory bound to compute bound when n exceeds 380. But here's the problem. At a resolution of 1K by 1K, both the compute bandwidth and memory bandwidth fail to reach their full potential. This is because we have a relatively low cache hit rate within our naive implementation. Note that each entry in the matrices A and B needs to be accessed multiple times. But if they don't reside in the cache, our memory access count can get close to 3n cubed rather than the expected 3n squared. This complication can be problematic when n is large, as the cache is less likely to keep the data when the same entry is accessed the next time. However, if you have a relatively small matrix, there's even a pretty high chance the entire matrix can be accommodated within a large cache. So, increasing the cache hit rate, huh? Where should we start? Introducing the first trick: transposing one of the matrices from row major to column major. This small adjustment makes our algorithm around 3 times faster. But you might be wondering, are we doing more computation when transposing the matrix? Well, this brings us to the two principles of cache optimization: maximizing spatial locality and temporal locality. In our original GEMM implementation, both of these aspects are suboptimal. You see, in the vanilla GEMM, both matrices A and B are stored in row major order. However, when performing the matrix multiplication, matrix B is accessed along its columns. This means that the algorithm needs to skip an entire row to access the next value. But wait a second, it's not like truly random memory access, so a modern cache system can handle this pattern, right? And you'd be correct. Actually, Your CPU likely employs prefetching as long as you have a stable memory access pattern like this. The problem is that you don't cache a single float when you access the value, but cache an entire cache line. The way you access matrix B results in a substantial amount of cache being brought in but not fully utilized. Therefore, the low spatial locality, in this case, leads to inefficient cache line utilization. Transposing the matrix B, despite the more computation and even memory access overhead it incurs, significantly improved the cache line utilization and therefore increased the overall performance at the end of the day. So we can improve the spatial locality by transposing the matrix. What about temporal locality? To improve temporal locality, we must first understand what caused it to be suboptimal. In the context of our matrix multiplication, every entry in matrices A and B needs to be accessed multiple times. However, when dealing with large matrices, holding an entire row in the cache can be challenging. So how can we make this memory access more efficient? Here comes the magic of linear algebra. Each entry in the result matrix Cij equals to the sum of Aik times Bkj for k from 0 to n. But if we divide the matrix into L blocks, the entries still equal to the sum of multiplication within each block. And when you really think about it, you will find we are actually doing matrix multiplication in blocks. Each block multiplication is essentially another smaller matrix multiplication. Why is this useful? Well, imagine if we choose a block size that's small enough to fit entirely inside a cache. Ideally, by doing so, we'd only need to access each entry in the matrix L times instead of n times. Take a look at this code snippet. While it may appear to have more nested loops, the total number of floating point operations remained unchanged. What we've achieved is a significant improvement in the memory access pattern, resulting in a better temporal locality. By breaking down the matrix multiplication into smaller and cache-friendly blocks, we can maximize the reuse of data stored in the cache, thereby accelerating our GEMM algorithm. That's enough for the concept. Let's turn our attention to the practical side, performance. Sadly, using blocked GEMM can be a little bit more challenging than the transposed GEMM, since you need to decide what block size to use. Remember, the actual number of memory accesses is the product of total size of two matrices, 2n squared, and the number of memory access for each entry L. Choosing a small block size will result in a large block number L. Therefore, the total number of memory access 2n squared L can approach the worst case memory access time 2n cubed. On the other hand, selecting a block size that's too large to fit inside a cache may negate the advantage of using blocks altogether. In practice, different machines may prefer different block sizes, and the only way to find the best block size is through experimentation. Another important difference between the blocked GEMM and transposed GEMM is, well, we don't need to transpose anymore. Our goal is to fit the entire block inside a cache. Moreover, people often tend to choose block sizes that are integer multiple of cache line length. So transposing the matrix won't improve the performance, right? Let's transpose it to see what happened anyway. The performance increased again. That's a little bit unexpected. As I mentioned earlier, transposing matrix B doesn't fundamentally change the cache line utilization. Instead, it improved the performance by affecting another parallel mechanism, SIMD. You might have noticed that I added an OpenMP SIMD macro just before the innermost loop. This seemingly small addition enables the compiler to leverage SIMD instructions for dot product calculations within the blocks. Now, if you've been following my previous videos, you are probably familiar with SIMD's capabilities. It can perform multiple floating point operations in a single CPU cycle. But there's a catch. It depends on efficiently loading data into SIMD registers. For the blocked GEMM without transposition, the innermost loop direction only aligns with matrix A. But after transposing matrix B, we can load both matrices into SIMD registers easily. Now, Let's explore another counterintuitive but highly effective optimization technique, copying blocks into local buffers. In the code you see, we've made a significant change by hard-coding the block size into the algorithm. This provides the compiler with more information for compile time optimization. However, the real magic lies in our ability to create local copies of data for each block. Copying data is often considered an expensive operation, but in this case, it almost doubles the performance again. The reason behind this approach is once again related to cache optimization. Notice I use the align as keyword when allocating the local buffer. This ensures that all local buffers start at addresses that are multiple of 64, which is the length of the cache line on my machine. Remember that every time you access an address, the entire cache line containing that address gets loaded into the cache. By making sure that our data structures align with cache lines, we'll again increase the cache line utilization. The next reason we are using local buffers here lies inside this OpenMP thread private macro. You might recall our discussion about force sharing in the last video. When two threads try to access the data on the same cache line, performance can plummet. Even without locks or other software limitations, the hardware often interferes to synchronize cache line between different physical cores, causing performance degradation. To solve this issue, we need to guarantee that not only does each thread have its own private data, but also these data blocks reside on different cache lines. I know it sounds a little bit stupid when I said, just keep them on different cache lines. But the solution is really that simple. Just use the OpenMP thread private macro. It copies a private buffer for each thread it spawns, and also handles the force sharing concern perfectly. Looks good. But there's actually one more problem we can solve: matrix transposition. As discussed previously, the performance gain from transposing matrix B is mainly attributed to achieving alignment with the innermost CMD loop in both local A and local B. However, what if we could achieve this alignment without matrix transposition? It turns out we can. If the matrix B is not transposed, the code will look like this. But hold on a second. There are still two local buffers aligned the same way: local B and local C. Actually, instead of transposing the matrix to let the buffer align with the loop, we can swap the loop to let them align with the buffer. This adjustment doesn't affect the computational logic of our algorithm. It merely transforms the access pattern of the buffer. And now, we can get rid of the annoying matrix transposition step. There are also some minor details you can fine-tune in your GEMM implementation. For example, we can clear local C less frequently by moving the clearing step one loop outward. All these efforts led to a substantial performance improvement, reducing the time needed to process a 1K square matrices from 1900 milliseconds to just around 16 milliseconds. That's an impressive improvement, I have to say, especially considering there's no stuff like fancy GPU acceleration. The bad news is that you probably don't want to optimize GEMM or any other linear algebra operations yourself, because there's a much better option called basic linear algebra subprograms. The Intel MKL implementation of BLAS can get you only 2 milliseconds for a 1K resolution square matrix GEMM. Plus, it also supports matrix multiplications between non-square matrices, unlike the crappy demo we showed today. But you get a point. MKL is also using similar approaches we used today somewhere in their proprietary codebase. You said you want to know what makes it even 8 times faster than the best we could do? Well, I did learn something during that high throughput optimization course I took last semester, including separating the block hotspot into another module and using assembly intrinsics to optimize it like crazy. And my professor also mentioned that even loading data into CMD registers in different orders can affect the performance. But I never use them in my own project, so I say I doubt if I can tell you anything about it. Anyway, if you enjoyed this video, remember to subscribe to the channel. As always, I hope you catch well, and see you in the next one.